is 2.6 of our study of K in modal logic, soundness of the tableau. Soundness means that every proof theoretically valid inference is also semantically valid. So what that means is proof theoretically valid, remember, are the tableau that we invented. The semantically valid is when you're worried about true or false. So to say that something is a system is sound is to say every time you use the rules of the branches that we learned about, then you will never get anything with these branches that you end up down here that are not also true or false based on what they should be based on semantic validity, right? In other words, if you start off with well, let me get a different. Let's say we start off with possibly A, and at world 0, and then we have to get 0 is related to 1 and A1. What that means is after we've gone through all this stuff, this doesn't actually mean A1 is true at world 1. It's not actually what it means. It's just A at 1. That's all that means. It's 0 or 1. That's all that means. Well, what we're going to prove, what we want to prove is every time we apply one of these rules in our system, that all these 0 related to 1, all these kinds of number related to number are actually world related to world. World 0 is really related to world 1, and A is true at world 1. So let's say this is world 1 and world 0. World 0 is related to world 1, and A is actually true at world 1. Yeah, that's what we want to prove. If possibly A is true here, we want to say that that 0 is actually related to some world 1, and A is true at that world 1, just based off of this. That's what the proof is about. And so and one of the reasons you can see probably is it isn't so easy as it was when we were just doing propositional calculus, right? They're not the ones and the zeros that we're working with now. So we're relying on this guy over here to show us the way. But if we're going to rely on this, then we're going to have to show that it doesn't come up with any errors. And that's what we're doing in this video. Alright, let's start off the proof with some definitions. First, I, squiggly I, crazy I, is the ordered triplet of W, the set of all worlds, R, all of the relations, and V, the truth values. That thing right here, this thing right here, is any modal interpretation. That's one definition. This just means an interpretation, a modal interpretation. I is a modal interpretation consisting of these things: all the worlds, all the relations, and all the truths. B, for this part of for the soundness proof, is going to be any branch of the tableau, any branch that you have. I is faithful to B if and only if there is a map F from the natural numbers to W such that for every node AI on B, A is true at that place in I, and if I or J is on B, then Fi, R, Fj in I. That's basically this right here. We have from the natural numbers like zeros, ones, twos. We have a map, right, where you have the 0 here, 0, world 0 here, 1 here, world 1 here. Every node on this branch right here we're saying that every node, that thing is true at that spot on that node. So here we have 0. The node, this node is at 0, and the map shows you right here. This is what it's talking about. World 0, and yeah. And by the way, map. When we say map, all we really mean here is like a one-to-one correspondence. For everything here, there's something over here, right? So 0, there's a world 0. For 1, there's a world 1. And at each of these nodes, if you have any formula, then that formula is true over here. So possibly A is true. Over here we have a node A at 1. Here we're going to say the node, the actual thing, the spot on the map that pertains to this node, to this natural number 1. Whatever formula is there is true at that place. And then of course 0R1, this thing maps to this right here, to that relation right there. So that's what I being faithful to B is. All right, now we'll start off then. We started off with a definition. We'll continue on with a lemma. A lemma, remember, is something that you're going to prove on your way to proving something that you really want to prove. And here's what we're proving. If, first of all, I is faithful to B, and a rule is applied to B, then it produces at least one extension B prime, such that I is faithful to that extension B prime. Alright, so what that's getting at is, again, looking back on our little map here, we started, here's the initial list right here. This is where we started off with possibly A1, possibly A at 0, excuse me. Possibly A at 0, and I have like a love sack here for 0, sorry about that. Possibly A at 0, we're saying if I is faithful to this initial list, then it's going to be faithful to all the stuff that shakes out from that list according to our rules for the Tableau. And meaning, in other words, I guess one more time I'll say this. So meaning that it's faithful, meaning that, if I have a 0 and a possibly A over here, there's going to be something over here where possibly A is true, and then every rule that I apply after that, we're saying that you're going to have, another thing that another place on the map over here, and whatever's here is going to be true there, and then these relations are all going to match up, all that. That's what we're saying. So remember how we did this lemma is we just went through every single rule. When we did it for the propositional calculus, we went through every single rule in the connectives and showed that every time we start off with something with that connective, we applied a rule to it, everything that resulted from that worked. Right? Everything that resulted from that was true. So I'm not going to go through every single one of the connectives that we did in the propositional calculus, because you'll see that it's pretty much the exact same thing. So I'll do one to show you how it's a little different, and then I'll do the new ones, the boxes and diamonds, which is what we really care about. But yeah, if you want to know how the rest of them work, watch this part and then look back at the other video, and you can see how I did all of those, and just change them accordingly. So first, we're going to assume that F does show I faithful to B. Right? There is that map from all the the initial list of stuff that you have, which is going to consist of this thing right here. So we're going to assume that I is faithful to B, and that there is like a map from this to a real place I, and and if A then B being false at that place. And we're going to assume that this occurs on that B. And other things might occur on the initial list, but for right now we're just worried about this one form of a thing that can show up there. Okay, so if this shows up on B, then based on our rule for the Tableau, we know that we'll come out with AI and not BI. We're just going to apply a rule to this thing that we first found on the initial list. Now we know that that this thing, this not if A then B at I, we're going to know that it that means since we said F shows I is faithful to B, there's going to be that map, right? There's going to be from this thing to an actual world I, W. That should be a W. Yeah. An actual WI where not if A then B is true. Right? This should be a parentheses. Yeah, so that's just what we said at the very beginning. So we haven't proved anything with that. We're just, we already said that. And then if not if A then B is true at that place, then based on these rules, the truth rules, we know that if A then B is going to be false at that place, which is just this rule right here, applied to rule 4 right here. So we apply this to 4 and we get this thing right here. And then that means that based on this rule right here, A will be true and B will be false at that place, right? If A then B is false, if A then B is 0, then I know that A cannot equal 0 and B cannot equal 1. So A must equal 1 and B must equal 0. Yeah, so A is true and B is false at that place. And if B is false at that place, based on this rule right here, I know that not B is true at that place. So I have A is true, I have not B is true, and here is applying this rule right here is where we get these guys right here, right? We said that at this place, not if A then B is true, and then we got these two things at the same place at world WI, and we just showed right here, well, if that's the case, then A is going to be true, and not B is going to be true there too. So we just showed that this soundness lemma works for the not if A then B at I. There is that map that goes from this node and this I, to this real place where this is true, and this is true. Okay, and the rest of those will work pretty much the same way. Let's go on to the more difficult ones, the boxes and diamonds. First, let's go with not possibly A, comma I. Right? We're going to show that if we assume that I is faithful to B, and you apply a rule to B, then at least one of the places where you apply the rule, one of the resulting branches, we're going to have I also faithful to that branch. All right. So assume that F shows that I is faithful to B, and assume possibly, not possibly, A at I occurs on B. So again, you're going to have a map from I to not possibly A is true at that place. Well, if that's the case, then here's the rule that we work out on our Tableau. Necessarily not A at I, just by applying rule number 2. By applying this rule, we have that on our Tableau. Now I know that possibly not possibly AI is true at f of I. Why? Because we've already said that I is faithful to that initial list. It's faithful to B, and this up here was on B. This is the extended branch that we created. So we've already said, let's just assume that I works for this guy, that there is actually some place, world I, and at world I, not possibly A is true at that place. Now here's another, this is also at world I, so we want to say, is necessarily not A true at this place? That's what we're proving. We don't have to prove this because we've just assumed that. And we're saying, assuming that that's true, is this also true down here? Well, we know that possibly not possibly A is true if and only if necessarily not A at that place is true. And how do we know that? We had this proof that was in a couple of videos ago, I believe in semantic validity. Yeah, it was in semantic validity, where I showed you how these two are truth value equivalent. I said there's an intuitive way you could just look at it. It's not possibly the case, then it can't be the case, right? Necessarily not the case that A. So if it's not possibly the case that triangles are four-sided figures, then it must not, and necessarily not the case that triangles are four-sided figures. That seems to make sense at an intuitive level. And here's the proof of how that works out. I won't go over it. Just look back on that video if you don't remember how that works. So we know that necessarily not I is true at f of I by the equivalence proof. And then so f shows I faithful to B prime. Why? Because oh, I think I skipped a step here. Yes, I skipped a step here. So no, I didn't even skip a step. We did not need this little guy over here. Yeah, that's right. So this was not necessary, this little these v's, because we don't have to worry about translating anything. We translated it with this guy. We said these two truth values are equivalent. So if these two truth values are equivalent, then we know that that this is true, this is also true. So we know that this is also here, necessarily not A. Alright, so F shows I faithful to this extended branch, B prime. Why? Because at this node, right, at this node, the formula is this thing right here. And remember, it's really confusing, I know, because I have an A here and I have an A here, and what this thing, this A stands for this whole thing right here. But yeah, at this node, necessarily not A, I, on B, necessarily not A is true at this place, F of I, at world I, in this interpretation. So this shows the soundness theorem is true there. For the next one, we have not necessarily AI. So again, we're going to assume the same thing. We'll throw up this rule again, and so we know that possibly not AI is on B prime. So appears B prime. We said that we're assuming, right here we said, we're assuming that for this, there is some world I where not necessarily A is true. And remember, these are just names, the world I, right? I'm not assuming that, we're not assuming that there is a literal place called world I, right? We're saying that there is some place corresponding to this, whatever that might be, you know, call it what you might. Okay, well, we know that, like I said, because it's faithful, we know that there is this place out here. That's what this step 4 is. And we know, based on the proof, once again, that these two things are truth value equivalent, right? That these two things are equivalent. That's something we've already proved. So we also know that this guy's over here, possibly not A, is true over here. So F is faithful to this B prime, this additional branch, because at this, again, for this node right here, where this is this A right here and I is this I right here, A is true is this thing right here at F of I, which is this world right here. So F shows that I is faithful to B prime. Alright, let's show that it holds for necessarily A at I. Again, assume that necessarily AI occurs on B. Here's a little trickier. Alright, what this says is that every time, you know, if you have this, every time you see IRJ, then you will have an AJ. So J could be, you know, let's pretend I is, you know, world 0 right here. Well, J could be 1, and there could be a 2, and there could be a 3. So you could have a 0 related to 1. You could have a and then you could have a 0 related to 2. Let's do this over here. And then so you would have an A at 1, and you would have an A at 2. Right? So every time for all J, for all numbers that could be over here in J, such that I is related to that J. So in other words, whatever this node is, whatever this number is right here is related to that number on B. A is J on B prime on this this extended branch right here. Right, that's what you're attempting to prove. Is every time you get this, you get let me erase this too. Every time you get a new IRJ, where you know these two I's are the same, it doesn't matter what the new J is. You're going to have something new down here. You're going to have an AJ down there in the extended branch. So we know that if there's some, for all IRJ, we've applied the rule, and we've gotten all of our AJs, and let's just pretend that there's only one world so far. Let's pretend that, and we have this, right? We know that necessarily A is true at some F of I. Why? Because we have the faithfulness, right? So there's this map where I is true at I corresponds to some world. We'll call that world WI, and at that place necessarily A is true at that place, at world I. That's what this rule says right here. For all j such that I or j is on B, there's this actual relation. So what that's something, again, something else that we've assumed. Everything above this line, everything in the original branch, you have a real correspondence, a one-to-one correspondence. So because this is on that initial branch, we're assuming that this relation holds. We're assuming that there is a wi arrow wj. There's some world that's related to some other world that corresponds to these two things. And so that is something that we don't have to prove. We're just assuming that off the bat. And now, let me see. A is true at f of j. How do I know that A is true at f of j? Right, this thing right here. We're trying to say that this thing is true right here. Well, we've said that necessarily A is true at f of I, right? And so necessarily A is true at this world. And we say that this world is actually related to this other world, right? That's this thing right here. So the rule over here says if you have necessarily A true at a world and that world is related to some other world, then A must be true at that other world, right? So we said here necessarily A is actually true at this place, and this place is actually related to this other place. So by this rule right here, A has got to be true right here. So we know that based on this definition right here. Well, then we have exactly what we wanted, right? The J corresponds to this, the A corresponds to that. Oh, it is part of this map. This new extended branch is part of the map. Sweet. That's exactly what we're worried about right here. And finally, for the possibly A. Again, let's pretend it's on the map. And here's the B. This is the beginning of the branch. This is the branch B. This is the extended branch B prime. And so yeah, we have applied our rule, and we have some IRJ where J is new. Remember, since F shows I faithful, that there's actually some place. Let's put it over here. World I, where possibly A is true at world I. That looks nothing like a diamond. These are hard to draw. Alright, well, let me try one more time. There. Possibly A. Right? Now, this is what we start off with. This is the extended branch here. So I can't do what I just did. I can't say, oh, and by the way, since F shows I faithful to B, we also have this other world WJ that the WI is related to. I can't do that because this isn't part of the initial branch B. This is the extended branch, so I have to show that first. All right. So this is what I have. This is what I have in my new Tableau. And possibly A is true at f of I. How do I know that? Because I've already, like I said, I is faithful to B, and that's what this says right here. So that's what we showed. That's what we did right here. Oh, that was a lot to jump over. I didn't mean something's wrong with the animation, but we will survive. So what this means here, possibly A is true at f of I. What that means, according to this, possibly A is true at world W, right, which is f of I. Possibly is true. That means that there is some W prime, some other world, such that this world is related to the original world, where possibly A is true, is related to that new world. And at that new world, A is true with that new world. So in other words, what that shows is there is some new world, and let's call that world J, such that WI is related to WJ, and so this part right here is that right there, and A is true at that world. So you know W prime, right? So A is true at that world. Alright? That's what we showed here. So, and now this gets a little more complicated, but yeah, let's define this new function then, f prime, which is exactly the same as f, except that this new map, at this new map, j equals world w, right? Well, f prime shows that I is faithful to b, because the only difference between f and f prime, but j is not on b, right? So in other words, we don't have this j up here, right, in this initial branch, and that's the only place where f prime and f are different. So I know that f prime is going to do all the work that f did, and one of the things that f did was show us that this was okay. So f prime is going to show us the same exact thing. Well, in this new f prime I is related to f prime j, which is this thing right here, right? Okay, this right here. And a is true at f prime j, so that is this world right here. And a is true, right? So that this is this a right here. So f prime shows I faithful to b prime. Our new function here, let me erase some of this extra stuff. Our new function here shows us that we had world I related to world j. That's what we wanted, because this thing is down here, right? So we wanted this, and our new function shows us that, and our new function has a true at world j. That's what it had, and that is this thing right here. So f prime shows I is faithful to b prime. Yeah, there that is. So that is the soundness lemma. We showed for every single connective, we showed that I is faithful to b, rules applied to b, then it produces at least one extension that I is faithful to. Right? Now on to the soundness theorem. For the soundness theorem, we're going to show that given some kind of set of premises, a finite set of premises, if you have that finite set of premises proof theoretically entailing a conclusion, then you will have that finite set of premises semantically entailing that conclusion. In other words, what we're showing here, what this means is, let's say you have, let's say your premises are something like possibly a at 0, or we'll say possibly a. Yeah, we could say possibly a entails a, right? So possibly a, then is it possible for you to have, to not have some world I? Oh, that's not right. Something like that, right? You want to say, like, if there's some branch up here, do the rules show you that that there's some kind of contradiction that you end up in down here? That would show us that this is valid, right? Well, then you will also have the worlds. That'll all work out too. Possibly a world or world 0. That stuff is all going to work out. Yeah. So assume that we've completed a whole tableau. Assume that we find that, and let's also assume, for the sake of argument, we're going to assume that the worlds don't match up. So in other words, we're going to show that the worlds don't match up, and if the worlds don't match up, then, and this necessarily doesn't also work, the tableau doesn't work, the tableau is open somewhere, then we will show that, oh, well, that means if you have the tableau closed, you must have this thing. Right? It's kind of, I think I showed you last time, it's kind of like that, if P then Q, not Q, entails not P, right? If you are in P, you have to be in Q. Oh, really? Well, then if I'm not in Q, I can't be in P, right? So that's what this is showing. If you have this, then you have to have this. So then, if I don't have this, then I can't have this either. So let's assume we don't have that, and we're going to prove that we can't have that either. So let's say that semantically invalid. What that means is that there is an interpretation that makes all the premises true and the conclusion false at some world. All right? That's just what it means to be semantically valid, or semantically invalid, excuse me. That you have all true conclusions and somewhere you have a all true premises and somewhere you have a false conclusion. Let f be any function such that f of 0 is that world where, in other words, f0 is the world where all the premises are true and the conclusion is false. Well, f shows I faithful to the initial list, right? That is the initial B part, right? Because we said 3 that there is some interpretation that does this, and 4 that that world we'll call as f0. Now, what we showed by the soundness lemma is if you apply a rule to the initial list, and that f shows that I is faithful to the initial list, then f shows I is faithful to at least one extension, right? So we apply a rule, we get a new branch, and we showed by the soundness lemma that branch is okay. That this is a legit branch, or at least one of them is. I mean, at least one of them works by the soundness lemma. So f shows I is faithful to the entire initial section, right? So if you have, some branch, and this initial branch, and we show that we said f shows that I is faithful to this branch. Then I have two new branches. At least one of these, we said right here with this part, at least one of these is set. At least one of these is faithful. And so let's say pretend it's this side right here. So we'll say that this whole thing is I is faithful to that whole thing. And then you keep going on and on and on and say, okay, well, let's say we have new branches. Well, at least one of those two things is going to be faithful. So that one is faithful. Something like that. So f shows I is faithful to each initial section of a whole branch B. If B were closed, if that branch were closed, then it would have some formulas of the form B and not B in some initial section of that. That's just what a closed branch is, right? You have B, and then let's say, pretend there's extra stuff up here, and then, you're going down, and then finally you get a not B, closed branch, right? So that's what it means to have a closed branch. And if that were the case, then in the real world, and these are initial, remember, this branch we said would be, based on what we just showed, would be faithful to, I would be faithful to this branch. So that means that there would actually be, if this is world 0 and this is world 0, there would actually be some real world 0 out here where B is true and B is false, which makes no sense, right? So truth value of the two would be 1, which you can't do, right? That's just in our truth value, formulae, we saw that the V of not B is 1 if V of B is 0, and otherwise it's 0. So that doesn't work out. So it's not the case that there are some formulas of the form B and not B in some initial section of B, so that B can't be closed, right? If there isn't a B and a not B, then that's just what being open is. So B is open. So if B is open, what that means is that you don't have sigma, you don't have all these premises and then the negated conclusion, and then that whole thing works, right? There's no contradiction in there, so there's no, that branch doesn't close off, right? So you have sigma, I'm sorry, yeah, I think I said that wrong. You have all the premises, you have not that conclusion, and there's no contradiction in saying that. So then, this is proof theoretically invalid. So we've shown from 1 through 16, if it's semantically invalid, then it has to be proof theoretically invalid. So we've also showed that if it's proof theoretically valid, then it must be semantically valid, which is what we wanted to show.